Hello, my name is Harsh Chima, and my presentation is going to be on containerization and OS security. So the market for container technology has seen an exponential growth as of recently. It's driven by the adoption of cloud computing and the need for efficient, scalable, and portable application deployment solutions. Organizations across various sectors are leveraging container technology to accelerate their digital transformation, optimize resource utilization, and enhance operational efficiency. The proliferation of these containers has led to the development of a rich ecosystem, including container orchestration tools like Kubernetes and Docker, which have become de facto standards in the industry. However, the features that make containers so advantageous also introduce specific security challenges. Unlike VMs or virtual machines, which have their own separate kernel, containers share the same host system kernel, creating a larger attack surface. This shared kernel architecture, while it is efficient, poses a significant risk as a single vulnerability can potentially compromise multiple containers. The exploitation of these weaknesses can lead to an unauthorized access, escalation of privileges, and ultimately the compromise of the integrity, confidentiality, and availability of the systems and data. In summary, while container technology offers numerous benefits in terms of efficiency, scalability, and portability, it also brings forth unique security challenges. Understanding these challenges and addressing these vulnerabilities in container security is crucial for safeguarding computer systems against potential threats and ensuring a robust, secure, and reliable operation in containerized environments. My hypothesis that's driving this research is the examination and testing of security mechanisms that are inherent in containerization, and trying to reveal vulnerabilities at the operating system level. By identifying these vulnerabilities, we can make robust mitigation strategies depending on the type of vulnerability to our OS security within containerized environments. Containerized technologies like Docker offer isolated environments for applications, enhancing the security and resource efficiency. The full scope of their interaction with the OS, particularly in terms of their security, hasn't entirely been well known or well drawn out. So this gap in knowledge could leave systems vulnerable to exploitation by malicious actors. My hypothesis is that an in-depth analysis to the inherent security mechanisms in containers is to examine them using a holistic approach by looking at both research papers and by using multiple vulnerability scanners to test the security of both a Windows and a Linux-based container. My hypothesis is that a Linux-based container will provide a more enhanced security than a Windows-based container because a Linux-based container has a widespread open source community, many of which are security professionals that like to update Linux images and provide even secure images that are Linux-based. Furthermore, my research will examine the performance of container applications, including the efficiency through network, memory, and CPU overhead, both before and after adding some basic system security hardening mechanisms on those containers. This holistic analysis approach aims to demonstrate the impact of security measures on container and performance, while also testing whether or not the security of Linux-based containers is greater inherently than Windows-based containers. So some related research starting with the paper Emerging Trends, Techniques, and Open Issues of Containerization provides an extensive overview of containerization technology. The authors discussed how containerization, by allowing multiple isolated user space instances on a single host, enhances load balancing, system maintenance, and energy and resource utilization. The review identifies challenges such as complex networking, persistent storage issues, security vulnerabilities, and scarcity of efficient management tools for container orchestration. Despite these challenges, the paper acknowledges the technology's potential, given its efficient virtualization capabilities demonstrated through extensive experimental comparisons with VMs and unikernels. The author highlights the need for a comprehensive literature review to bridge the knowledge gap between developers and existing container technologies. So, the paper really provides a detailed comparison between container performance against VMs and unikernels across several metrics such as CPU utilization, network bandwidth, execution time, etc. Using standard benchmarks to show that containers generally deliver satisfactory performances across most aspects. The paper concludes the discussions on the research challenges and future trends in lightweight virtualization, advocating for further advancements in security strategies, cross-platform support, and persistent storage solutions. Another research paper provides an in-depth analysis into container security. Container security projected a $2.7 billion market in 2020. So this research paper was conducted in around 2016, and they were actually right. It was projected, and it did reach that, and I believe it did reach even higher than that by 2020, and even higher still to this day. So the authors identified a security as a crucial concern impeding widespread adoption of containers. The paper proposed software-based solutions leveraging Linux features and security modules for 3 of its use cases, and hardware-based solutions like TPMs and Intel SGX for the last solution. Containerization significantly reduced resource usage and startup times compared to VMs, making them more suitable for IoT services, cloud services, and microservices. Despite the benefits, shared OS kernels introduce security vulnerabilities. The authors reviewed Docker's adoption as a leading container technology and then discussed the evolution from monolithic to microservice architectures and detailed a comprehensive literature review methodology that included a variety of sources from academic research to non-commercial reports. They were attempting to bridge the academics and the industry sector and hopefully come into a one standardized solution to an enhanced secure container. So, the paper discusses various Linux kernel features for container isolation and resource control, such as namespaces and CG groups, along with system call filtering and seccomp, and fine-grained access control via capabilities. The discussion extends to Linux security modules, LSMs, like SC Linux or AppArmor, which offered enhanced security policies. In terms of hardware-based solutions, the paper elaborated the use of virtual TPMs and Intel SGX for securing containers on potentially untrustworthy hosts. The conclusion of the paper basically reiterates the significance in containers, and they hope in future research avenues to address meltdown and Spectre attacks, which were common in VMs, along with the digital forensics of containers and the usability of vulnerability assessment tools. So that is where my research differs from many of these, as my research will introduce Linux-based containers on top of those vulnerability assessment tools that I will use for figuring out the security between the two OSs and how much they differ. Finally, the third research paper that I used directly for my paper, that is titled The Evaluation of Security Properties of Containerized Systems. The authors noted a lack of uniform approach for defining and verifying the security of systems despite the widespread use. They compared 2 models for defining security threats, one from the academic research and one from Common Criteria Recognition Arrangement, or the CCRA, and argued that both identify the same security parameter. So, this paper also looked into Linux kernel features such as namespaces and control groups that underpin container technologies and facilitate resource management across containers. They also discussed other types of attacks such as denial of system and other resource exhausting attacks, highlighting the need for effective countermeasures. This research was very similar to the last paper, as they used many of the security features within containers to enhance their security, and testing this performance metrics along with the enhanced security versus without it. But the paper suggests that the Docker security features satisfy the security model proposed through academic research by Reshetova, and it aligns with the security requirements outlined in the CCRA. So while it does meet the security features per academic models after enhancement, its security in the context of common criteria depends on specific configurations and operational environments. So it's basically depends on how and where you utilize containers, because it can become a security vulnerability if it's placed within an organization, perhaps a financial organization, and doesn't adhere to some of the CCRAs or the academic standards put out. And that could be a sort of avenue to leak into the network via resource exhaustion, or even worse, meltdown and Spectre attacks. And an adversary can pivot onto your network through that. So it really depends on organizational needs or industry needs as to how Docker is utilized. So the metrics that I used in my research paper was very similar to how the researchers that I read about utilized theirs. I wanted to measure the security vulnerabilities present within native Linux and Windows container images, basically bare images that have nothing on them, freshly downloaded. I wanted to utilize multiple different vulnerability scanners to get a more accurate reading, not so much as to find specific vulnerabilities, but to find if they all align with the results that they get with each other, and perhaps there's one clear-cut answer to my question, or my hypothesis, sorry. And then what I will do after I figure out those is add basic hardening and security mitigations, similar to what they added, but less sophisticated, only to see the efficiency, using efficiency scanners to see how optimized or the performance is after implementing those security defenses and hardening, to see how the performance gets varied. Another part of my hypothesis that I didn't mention was to see how much security would impact the performance, and by adding basic hardening procedures, if the performance doesn't change as much, then perhaps it should be almost an industry standard to harden immediately after installing such an image. My lab setup includes a Windows 11 home desktop with a Docker desktop that contains a basic Windows container image, along with a VirtualBox with an Ubuntu VM and a Kali Linux VM that both have Linux container images. This was the most efficient way for me to get the container and the bare container images that I could. So, my results are as shown. Apologies for the graph on the bar chart on the right. For some reason, every time I paste it onto the PowerPoint, it ends up on this weird formatting. But basically, the x-axis is the Docker operating system version, which is, as you can see, Linux and Windows. And on the y-axis is the number of vulnerabilities. Now, I'm not too concerned with the exact number as I am with the results. And I know Anchor results aren't shown, but it will be shown on the next slide when I perform after hardening is installed. But basically, Anchor also shows that Windows had more vulnerabilities present than Linux did. And there are actually 7 that I tested on using, 7 different vulnerability scanners that I use here. I think I added another one just for fun. And I believe out of the 7, 5 of them showed that Windows had more vulnerabilities than Linux, and the other two, the yellow and purple one, or Docker, it should be Scout, and Falco, have slightly higher vulnerabilities in Linux than in Windows. So here's an example of Docker Scout, which is a vulnerability scanner inherent in Docker Desktop, of me running an image, and 19 vulnerabilities were found in this Linux, and you could see the level of vulnerability, which is high, medium, and low, and then an example of a vulnerability where I pulled out the summary, and you can read about it, about which CVSS, which is the security vulnerability, the risk scoring of a particular vulnerability that was found in this. Just to show you how a vulnerability scanner looks for container images. Here is the use of 3 vulnerability scanners because I got the results that I needed. So I only used 3 here. Docker Scout, which is blue, green is Anchor, and red is Claire. And after the implementation, basic hardening reduced around, it was around a 9 point something percent, very close to 10. So around 9 to 10% across all Docker containers, just by implementing basic hardening, which was like adding network policies, I would like subnetting, reduction of, or adding passwords, complexity, very basic things which I've outlined in my paper what they were. And as you can see, Windows is still a little bit higher than Linux, but overall reduction did happen. And Anchor is on this, so you can see the results of Anchor as well in the green. So the conclusions, the findings of my study affirmed my initial hypothesis that Linux containers did exhibit fewer vulnerabilities compared to their Windows counterpart following initial vulnerability scanning. This outcome underscores that inherent security strengths of Linux-based container environments, which can be attributed to their design and robustness of the Linux kernel. And I would like to add, it probably is also attributed to the open source community, which the security community largely adheres or uses Linux. The reduced vulnerability footprint in Linux containers not only aligns with established perceptions about Linux security, but also highlights the critical role of underlying security operating system in container security. So the significant decrease in the vulnerabilities that I found, which was about 10% across all Docker systems, was achieved without compromising efficiency after testing for benchmarks. It was a very negligible amount of efficiency that increased. It was about less than, I think, 1%, 1 or 2%. And it did not compromise efficiency as much as I thought it would. I'm sure by implementing more stricter security procedures and mechanisms, the efficiency would probably go down, as that's what the trade-off usually is with enhanced security, such as more complex cryptography utilized via networking or password security. And so I would say the importance of integrating security practices into the container lifecycle, from image creation and deployment to runtime and orchestration, is definitely an understatement. We should, at the very least, all companies and organizations can implement basic hardening to enhance security, so that container images won't be such a security issue or vulnerability in your respective organization's attack surface. So yeah, these are some of the references these are all the references that I used, academic references, and that is the end of my presentation. Thank you. 2023.